So we go to GoDaddy, say, hey, I got remotesport.org here. You go to name servers, you hit manage DNSSEC, you paste in this little record, you do a simple lookup, it comes back against the Phreebird server, gives you the hash to put in. You say, go ahead and do it. You gotta wait 30 seconds, and then you're done. And then it's live, and then it's working, and then you can run end-to-end authenticated queries against remotesport.org 30 seconds later. This is actually kind of cool. So why does this work? Phreebird is an online key signer. Like SSH, SSL, and IPsec, it depends on a signing key being available whenever requests come in. There's an alternative where a magic key sits in a vault and you truck it out every once in a while. You alter things in DNS. In our real-world networks, we're changing stuff in DNS all the time. Phreebird, for performance reasons, actually has a cache. So when it applies signatures to some records, so a record might be this IP address is, the IP address for foo.com is 1.2.3.4. Or, I don't know, the certificate for foo.com has a hash of AABBCCDD. Phreebird will see responses come back and will sign them so that 1,000 requests for the same name will not cause 1,000 hits to the encryption engine. Now, DNSSEC was designed to allow offline key signing, and that is awesome. The two reasons why this is the case are, first, DNSSEC is old. I mean, DNSSEC was started in the 90s where high-speed processors and cryptographic accelerators simply weren't the kind of things that were available. Also, DNSSEC needs to operate at scale. So it needs to be able to simultaneously support the smallest of the smallest name server to the root operations that have a maximum security requirement to COM, which is just enormous. But not every server should be run like the root. It's a big deal that everyone can be, but that doesn't mean should be. Because the reality is, the biggest thing that made DNSSEC such a miserably complicated thing to deploy was having to do some massive pre-computation phase. When you have some massive preload happen, it turns out empirically protocols get orders of magnitude more complicated. And the best example actually is PGP or GPG. The amount of work that those code bases go into to managing their key rings are literally 95% of what's going on in there, with the other 5% being encryption, decryption, signing, and validation. It's enormous, and by going online, you get rid of the complexity. Now, there's some precedent here. We did not invent online key signing. I mean, look at all those other protocols. DNSSEC has been quietly including support for this design strategy for years. Ben Laurie is the guy behind it. Behind at least some of it. There's even another DNSSEC server that does this sort of lazy signing. That'd be Powered DNSSEC by Bert Hubert. What Phreebird has that's kind of interesting is that it uses the existing DNS framework, whatever it may be, and enhances it with DNSSEC responses. So it's just a proxy. It sits in front of your systems like a lump in the wire, and it signs. That means there's no operational impact. You manage your DNS just like you always have. There's no configuration. There's enough information in a DNSSEC request-reply pair to figure out everything that is needed in terms of the signatures involved. I wasn't sure it was going to end up that beautiful, but it turns out, yeah, it totally does. And it always returns the right answers. So you can have the world's most complicated name server that is like trying to return video over DNS, and I'll still sign it. No problem. Implementation notes. Today it's a UDP port forwarder. You've got to change the DNS port. If you don't even want to do that, sometime in the next week or two, I'm going to implement what's called Linux mangle table support. The name server will think it's sending an unsigned response, but something magic will happen in the kernel, and it'll be like DNSSEC on, DNSSEC off, DNSSEC on. So this stuff is fast. Don't look at me. I just wrote a few lines of code. The Linux kernel developers and lib event developers are awesome. Niels Provost is a badass. With a few hundred lines of code, you can today write a name server that will support 60,000 queries per second on stock hardware. Now, if you want to understand how fast 60,000 queries per second is, only a few years ago, that was all the queries that .com received in the world. So on one box, with this API approach, you're able to do what Com was doing a few years back. It's actually quite impressive. Now, we're not going to be that fast because we've got a back end to talk to, we've got to manage crypto, we've got to manage caching, but the experimental evidence suggests we are, by leaps and bounds, fast enough for all but the absolute biggest thing, and we haven't even tried to optimize. Phreebird is open source because you're just going to implement it anyway. We should have code out today, but we wanted to get all the demos done. So if you want a preview of what probably has some horrifying remote code execution flaws, feel and by probably, I mean like man. That's not a good use of popen. Seriously. Send an email to info@recursion, and you can make fun of me all night. Code should be out within the next couple of weeks. I am actually planning. Have you guys heard about these Pixel Chi displays by any chance? Fully sunlight capable. I actually got one out of Maker Shed. All I want to do in life is sit by the pool at the Palms, get a pina colada, bust out the netbook, and hack. Like, yes. So that should actually dramatically accelerate development of the Phreebird packaging. As a note, this stuff really is the 6 to 18-month timeline, so your mileage may vary in terms of deployments. This is purely so you can understand, wait, this technology is pretty cool. Now, Phreebird's doing a whole bunch of stuff I don't have time to tell you about today. I'd be going on for a couple hours if I did. There's a bunch of obscura, there's a bunch of things people have kind of wrung their fingers about DNSSEC. Questions like, how do you handle non-existent records dynamically? How do you tunnel records to the registry.org when, say, your registrar doesn't give you a web interface to be able to put what are called DS records in? What about time? How do you manage rollover and expiration? How do you keep clocks in sync? There's some very interesting problems in DNSSEC around what do you do about time, since everything has an absolute time. What I do have time to tell you now is this. All these problems are pretty easily managed. They took some work, they took some effort, but we've got fixes for all of them. And online, the recursion.com site, the answers will be posted. But I want to focus this talk on, hey, this technology is going to be awesome for your applications. So, okay, towards the domain key infrastructure. Perhaps DNSSEC is easy to deploy, but is it in fact useful? Distributed authentication is only interesting if it provides end-to-end semantics. My desktop to your server, or my phone to your phone, and so on. You might say, but Dan, I know a little bit about this stuff. I heard that all DNSSEC does is secure the link between these name servers that I speak to, but not like me and the actual end server. So what's going on here? Well, it turns out that was the original model of DNSSEC. They actually figured your name server would do all the hard work, and then it would send you a little bit called AD. And AD stands for, nah, it's cool, I checked it for you. It doesn't actually stand for that, but it really does. Look, I like Starbucks. I've known people who work for Starbucks. I like their coffee. I'm not trusting Starbucks to tell me whether it validated the certificate for Bank of America. Not gonna happen. There's no application on earth that's going to alter the user experience based on this little bit of context. Give me the proof or go away. So we have some normal end-to-end modes. First mode is called chasing. When you ask for www.foo.com, you can set a bit called CD, called checking disabled. And what you will get back is the answer and a signature saying www.foo.com was signed by foo.com. And then what do? Well, you go back to foo.com. And you say, well, what were you signed by? And it says, well, I was signed by com. And you say, well, how about you, com? What were you signed by? And it'll say, well, I was signed by the root. And then at that point, you have a chain from www.foo.com to the root. And in this model, you only talk to your local name server. Now, there are two problems with this model. It works about 90% of the time, but that's not enough. A 1 out of 10 failure is still operationally too expensive. The first problem is that it might get blocked by your local resolver. The deal is, in DNS, it's a lot of work to bounce around the internet, to go from root servers to com servers to yahoo.com servers. I mean, it takes some complexity. And DNS was designed in 1983 when such complexity was unimaginable to have on every single computer. So what they did is they said, okay, we'll take this hard work and we'll put them in these magic boxes called name servers. And these magic name servers, they'll go ahead and do all the runarounds. Well, what is happening in this situation is the box that's doing the runaround, not only might we not be willing to trust it to go ahead and do DNSSEC validation, but it may not know how to send us back a little bit of extra information about the key material so that we can do it. In other words, it ain't doing it, and we ain't doing it, so it ain't getting done. And so that's kind of a problem. The other thing that might be a problem is round trips. If I have to keep going back and forth with my local name server, that's actually a lot of round trips, and it can be slow. And as we know from experience, if you make a web browser depend on too many things that are slow, it will just not do what you ask it to. So in general, almost all web browsers don't go ahead and check to see if a certificate has been revoked. Someone's checking if certs are revoked, because apparently there's a couple billion checks a day, but your average web browser is not one of them. Revocation is a bit of a lie in X509. What we're doing about round-trip fixing in DNSSEC, and this is a project of Paul Vixie and mine, it's called SuperChase. In SuperChase, when you ask for when you say, hey, give me some signing information for www.foo.com, in SuperChase, it gives you the path all the way back to the root. Why? Because it has to know it anyway. If it was going to do the validation, it knows the chain. I'm just saying, hey, give it to me as well. And so we figured out how to make that happen, and it's pretty straightforward. Doing it's about 10 lines of code in LDNS. Part of the Phreebird release is going to include sample code. You just say chaser spooky.navy.mil.org, and you in fact get a path all the way back to root. Done. End to end. Another method is called tracing. Instead of chasing where you go up, tracing you go down. You're basically taking that magic box that does the running around the internet, you're embedding that in random applications with what's called libunbound. Libunbound is the name server built upon LDNS, and it itself is it takes about 3 lines of code in libunbound to do a secure resolve. It's super straightforward and easy. Now, some issues. Chief among them, if you have a situation where every device is going straight to the root, you'll cause the root to melt down in a pile of flames. What might make that acceptable, or at least make things better, is if the devices are actually caching information for serious periods of time and only updating the information when it changes. The root information doesn't change much, COM information doesn't change much, and so on. This, by the way, was the problem with DNS curve. Dan Bernstein's brilliant. You guys have no idea how much time I spent arguing that people should do his stuff. However, if Dan Bernstein's approach, the only way to get end-to-end trust was to bypass the local caches all the time, always go to the root, always go to the COM servers, they would have melted down. And of course, those middle boxes, worst at hotels. There's nothing worse than hotel networking. When you're at a hotel, be glad you can go to Google. It's surprising. Hotel boxes will still mess with tracing operations. So, HTTP is the universe's universal tunneling protocol. You can actually do DNS over HTTP. DNS over HTTP basically involves doing GET requests with DNS in the actual URL that is requested. Phreebird does implement this. Obviously, you can tunnel stuff over DNS, over HTTP, because everyone tunnels stuff over HTTP. The only question is, what's the performance impact? So, what do you guys think? You think, tunneling everything over HTTP is going to have like a 10% hit, a 50% hit, an 80% hit? Yeah, well, For whatever reason, it seems to be faster. What? Yeah, no, 3,200